Hi everyone, my name is Neha Kartham, and in this lecture we are going to learn about digital electronics. So these are the topics which we are going to cover in the lecture. First is analog versus digital, then why to use digital or analog, generating a digital signal, multivibrators, defining logic levels, testing for digital signals, using a logic probe, and then mounting ICs. Now let's start with the difference between analog and digital. Analog signal is that signal whose output varies continuously in step with the input. As you can see here, this is the analog device. Input signal is coming into the device, and the output of the signal looks like this. And you can see here in analog signal, time versus voltage graph is very smooth and it is continuous. While these signals may be limited to a range of maximum and minimum values, they are still an infinite number of possible values within that range. For example, the analog voltage coming out of your wall socket might be clamped between negative 120 volts and positive 120 volts. But as you increase the resolution more and more, you discover an infinite number of values that the signal can actually be. And that value could be anything, for example 68.72, 68.63, 68.77, etc. So that's your analog, and the example for analog device could be the light dimmer. As in the light dimmer, it can make the light control by varying the brightness anywhere within a defined range of values. And next we have digital signal. So digital signal is the one whose output varies at discrete voltage levels, commonly called high or low. So these digital signals, they must have a finite set of possible values. Let's first see the digital device. You can see here this is the digital device, and then the output signal is coming out. So you can see how the output varies between high and low. So this is your low and this is your high. So the output basically goes between high and low, or you can say 1 and 0. So the number of values in the set, it can be anywhere between the 2 and a very large number. That's not infinity. Most commonly digital signals will be one of two values, like either 0 volts or 5 volts. So the graph which you see here, this timing graph, it looks like a square wave. Or you can say this is a digital signal, which might be a discrete representation of an analog waveform. Now next is why to use digital devices. So the digital devices, they are used in all aspects of our lives and in all different workplaces. For example, in our personal lives, and while at school, we use digital devices to educate ourselves, to entertain ourselves, and to socialize with friends and family. If we see computer hardware, then it encompasses digital devices that you can physically touch, which includes like desktop computers, laptop computers, mobile phones, tablet computers, e-readers, storage devices such as flash drives, input devices such as keyboard, mouse, and scanners. Output devices such as printer and speakers. So all of these devices, they contains digital circuitry, and which has the ability to store the data, and digital devices, they can do the calculation also. So if you see the digital calculator, they can easily do the computation in few seconds. They are compatible with display technologies, they are compatible with computer technologies, systems can be programmed. Digital IC families make design easier. So these digital ICs, they are very small in size, and despite of their size, they can do multiple operations, and you will get to see that in the microcontroller class, and you will be amazed that how a small IC can perform different operations and can make the hardware work. So it is very amazing that with the help of these digital circuitry, we are able to reduce the size of the devices. Now next we have analog. Why to use analog? So the most real world events are analog in nature. For example, human voice in air is also analog signal. And there are many analog devices which are present, for example, thermometer, tape recorder, analog wall clock. In your lab, you use analog multimeter, in which when you change the knob, then you will see different values of the voltage or the current. These analog devices, they are simple in design. Their speed is fast, but not as fast as digital devices. The analog devices, they are more likely to get affected by the noise, and their hardware is not as flexible as digital hardware. Traditional electronic system were mostly analog in nature. So most of the previous devices, or we can say commonly electronics devices, when they were invented, they were analog in nature, and then the digital circuitry was introduced and made the circuit more simple, compact in size. Now next is generating a digital signal. So here you see there are two ranges. First is the low range. This defines the low range, and here it is a high range. And there's a mechanical switch which is connected here. There's a mechanical switch here, and then you have this 0 volts which defines the low range, and this 5 volts which defines the high range, and in between them is the undefined range. So let's see, when the mechanical switch is connected to the 5 volts and goes from 0 to 5 volts, then this kind of analog signal comes out, and based on this analog signal we will see what will be our digital output. So let's start from here. So when it goes to the top, then that means it is high. The same you can see here, it is high, and then it goes to the lower range. So when it hits the lower range, then you have the low, and further from lower range it goes to the high, so that's why you have this high. And then here comes the interesting thing, because after going from high, it goes to this undefined region. You see here, this is the undefined region. After going into the undefined region, it comes back again to the high. So what we have, high and then undefined region, and this, and then again high. So this undefined region between high and low, it may cause trouble in digital circuits, and it should be avoided. To avoid this, what we can do, we can use mechanical switches. They are sometimes demounced. So let me show you. So we use a debounce switch. This is the block diagram of the debounce logic switch, and as you can see here, this is the mechanical switch toggling between low and high. So you can see now it is low, so it is the low range, so it is latching the output which is coming here, and then when it is again high, then latching it at a higher voltage, and then again low, and so on. So here this the use of debouncing circuit or latch is very beneficial. Some of the mechanical logic switches which you'll use in the lab, they will be having the latch circuit, and these latch circuits they are also called flip-flops. We are going to see some of the debouncing latches in the next slide. So we have this one-shot multivibrator. This is also called a monostable. It is an electronics device that emits a single pulse when triggered. And then we have a free running, which is called astable multivibrator. It is an electronics device that oscillates between two stable states, which is high and low, and it is commonly known as a clock in the digital system. So we'll be using a clock when we learn about different sequential circuits. So whenever the clock comes, then you have to keep in mind that you are using a multivibrator to generate a clock. And then we have the latches. It is an electronics device that has two stable states, high and low, and must be triggered to jump from one to another. They are commonly known as flip-flop and commonly used as a temporary memory. So let's see how a digital pulse is produced in a one-shot multivibrator. So here this is a multi-shot vibrator. So as this switch goes down and connects to the supply, then one shot is created, and the length of the shot is depending upon the circuit of the multivibrator. So as you can see, as the mechanical switch went down, the signal is produced, and the output pulse width is determined by the multivibrator and not how long the button is pressed. Now let's see the free running multivibrator. As you can see, the input is connected to the supply, and through this multivibrator you see a continuous clock is produced. So this kind of clock we'll be using in this later sequential circuit, and you will see the benefit of this clock in the later lectures. Now let's do some tests. Question 1 says dash it could be astable or monostable. Multivibrator is an electronics device that generates a continuous string of digital pulse. It may also be called a clock or a free running multivibrator. So what would be that? Astable or a monostable? So monostable was a one shot. So definitely this is not going to be a monostable. So the answer is astable. Now next is a dash multivibrator is an electronic device that generates a single digital pulse when triggered. So this is a monostable multivibrator. And then a dash multivibrator is an electronics device that has two stable states. It is also called flip-flop and is used as latch to hold data. So if you have a flip-flop, then it is a bistable multivibrator because it has two states. And then last, dash multivibrator is an electronics device that is sometimes called a one-shot multivibrator. So definitely it is a monostable multivibrator. So there it is. Now let's see defining the logic labels. So how we define the logic label, it is important. So these logic devices interpret input voltages as either high or low. the most commonly used are the TTL or CMOS. So TTL basically stands for transistor logic, and CMOS stands for complementary metal oxide semiconductor ICs, and they have their unique voltage profiles. Both TTL and CMOS ICs input voltage profiles are shown below. So this is the voltage profile for TTL and CMOS. So before we see their voltage profile, let's see what is TTL. So TTL is basically built from BJT, which is a bipolar junction transistor, and they are widely used in applications such as computers, industrial controls, test equipment, and instrumentation. They are manufactured by many semiconductor companies. For example, you will see in the lab that 7400 series, which is basically manufactured by Texas Instruments, and that is one of the popular TTL. TTL power consumption is higher when compared with the CMOS. Whereas CMOS, which is called your complementary metal oxide semiconductor, it is a technology for constructing integrated circuit. So this CMOS, it is used in microprocessor, microcontrollers, static RAM, and other digital logic circuits. They uses a symmetrical pair of P-type and N-type MOSFETs, and it has a high noise immunity and low static power consumption. So both TTL and CMOS circuits, they have like 4 electrical characteristics. So right now we are not going to get in detail of those characteristics. We will just focus on the voltage profile. So if you see the TTL, so these TTL, they operate on a nominal power supply voltage of 5 volts. Ideally, TTL, they have signal, high signal, which would be 5 volts, and low signal, which would be 0 volts. Practically acceptable input signal is between this range, which you see, the lower range is between 0 to around like 0.8 volts, whereas the input acceptable input, high level input signal here, this range will be between 2 volts to 5 volts. So for example, if a voltage signal ranging between 0.8 volts and 2 volts were to be sent into the input of a TTL gate, then there would be no certain response from the gate, and the signal will be called your undefined, or the it will called as a invalid state. So this trouble range for output signal levels, they are narrower than for input signals levels, and the output signal level range is from 0 to 0.5, and the high at the higher end it is 2.7 to 5 volts. So this range is made to ensure that any TTL gate outputting a digital signal into the input of another TTL gate will transmit voltages acceptable to the receiving gate. And the difference between the tolerable output and the input ranges is called your noise margin of the gate. Now here, on the other hand, if you see the CMOS family, in the CMOS, the acceptable input signal voltage ranges from 0 volts to 1.5 volts. This is for the low logic, and for the high logic or the high states, it is 3.5 volts to 5 volts. So you can see that how input acceptable input input voltages is different for CMOS when compared to the TTL. CMOS input voltage for high logic is narrow, from 3.5 volts to 5 volts, whereas it was 2 volts to 5 volts for the TTL. And the lower range is higher too. In this case from 0 volts to 1.5, whereas here it was 0 to 0.8. And in CMOS, if we see the output signal voltage means if you have a CMOS, then the output signal which is coming out from the CMOS, that acceptable range is different. For the lower range, it is 0 to 0.05 volts, and for the higher logic, it is between 4.95 volts to 5 volts. So here the advantage with CMOS is that they can be powered voltages as high as 15 volts, and the noise immunity for the CMOS is better than TTL. Now let's see next. This is the test. First question says an input voltage of 3.5 volts to a TTL IC, which has a voltage level of 5 volts supply would be considered a high, low, or undefined logic level. So you remember for the TTL, the input voltage level, if you see the lower side, it was 0 to 0.8 volts, and for the high side it is 2 volts to 5 volts, and this voltage is 3.5 volts, which means it lies between 2 volts to 5 volts, which is the high logic. So that's why the logic level is going to be high. Now let's see next. An input voltage of 0.5 volts to a TTL IC would be considered a high, low, or undefined. So 0.5 lies under 0.8, from 0 to 0.8. So this is going to be low. An input voltage of 1 volts to a CMOS IC, which is of 10 volts supply, would be considered a high, low, or undefined. So here we are talking about 1 volts, and you remember the range for a CMOS for lower range was 0 volts to 1.5 volts, and the higher range was 3.5 volts to 5 volts. So this input voltage is positive 1 volts, which means this is going to be low level. And then we have the input voltage of 9 volts going into the CMOS IC, and the supply is 10 volts, which means the higher logic here we are going to have is from 3.5 volts to 10 volts, which definitely lies into that range, this 9 volts. So we will consider this as a high logic. And last, we have an input voltage of positive 1.5 volts to a TTL IC, would be considered as a high, low, or undefined. So again, we know that the input voltage going into the TTL is the range is from 0 to 0.8 and 2 volts to 5 volts for high logic. So for low logic, this 1.5 volt is not falling into that range, in the low logic range. So this is going to be undefined. It is between 0.8 volts and 2 volts. So this is undefined. Now next is testing for a digital signal. We're going to see LED output indicators, logic probe, digital multimeter, oscilloscope, logic analyzer. So let's start with transistor driven LED output indicator. So as you can see here on the screen, that this is our transistor. which is connected, the collector of the transistor is connected to the LED and a 150 ohm resistor and further to the supply of 5 volts. And then the base of the transistor is connected to a 10 kilo ohm resistor, and further there is a mechanical switch, and then it is connected to the supply of 5 volts, and the emitter is grounded. So right now this mechanical switch is connected towards the ground position, which means in this position the LED will not be light up because the sufficient voltage is not reaching to the base region to turn this on to provide the current to the LED. Now what will happen when we mechanically put the switch to the 5 volts battery, then the current will goes into the base of the transistor, and then the sufficient current will be provided to turn on the transistor, and once that happens then the LED will be turned on. Now next we have logic probe behavior versus logic levels. So here we are going to have the most basic instrument for testing the digital logic level is the logic probe. So as you can see here, this is the logic probe, and we're going to see different conditions when we test this logic probe. So when logic probe is connected to the lower level, then the logic low indicator will brighten up. As you can see here, the test point is connected to low region in the CMOS. Now in the second case, when it is connected to the high region, then the indicator is different, and this indicator shows that the logic is high. And when both of the regions are connected to the test point, then this type of situation is called the floating. This is called the floating indication light, which means the output is undefined. It is between the high and low. So if that happens, then this third light will turn on. Now logic probe dynamic response. So as you can see here, the digital signal is going into is being tested. So if that happens, the signals goes from high and low, and that's what you saw, that how the light was blinking at the high point. So this says the same thing. The probe toggles between high and low. Now next, if you have a signal something like this, even so you can see how it is transitioning between the low and high. So here the probes probes stretch narrow pulses, so they are not missed. So you can see these pulses, they are narrow in size, but they are not missed by this test probe. It is still counting these as high. And again, this is a situation of a toggle in which it is testing high and low, and that's what you saw in the indicator. Now again, this is a different kind of digital signal. You can see how consistent it is. High and low signal, their frequencies, their frequency is very high. So if that happens, then again this is a toggle situation. Now mounting ICs. So if you have there are two ways to do that. This is a through hole type. So as you can see, this is our PCB, and these are the two holes, and you have put the IC. You can put the IC in this way. When you do that, the leads will come out, and this is where you do the soldering in these two holes, and you will do in such a way that it forms a conducting path. Now next we have mounting the IC using the surface mount technology. So you can see that how the IC has been placed on the printed circuit boards, and these are the conducting parts. And if you want to connect the IC, then you have to solder at these terminals. So by doing this, the device placed by automatic equipment. So this automatic equipment, they are used to place these devices so that they are placed accurately in the on the PCB board. Boards cost less. Fewer holes are required in this type of technology when compared with the through hole. In that, that consumes more space. With this one, the space is really can be saved up. And higher connection density is possible with this type of technology. This technology also has a smaller and this has a smaller and less expensive products. However, with the surface mount technology, if anything goes wrong, then to repair the component is very difficult. So for example, if this IC goes bad, then to take this IC off is difficult, and sometimes while doing in that process, the IC damages its IC pads, these damages. So repair is difficult in case of surface mount technology, but it is a much better approach to make a circuit. Because you can utilize the board and you can put more components, and your design can be more compact. So this is the end of the lecture. Thank you so much for watching.